So yesterday we had actually defined what these are, and I presume we had even done hybridization of we went as far as this particular, as far as solving the okay. So we finished this part of identifying, show the kind of orbital overlaps that is using the SPN to S and SPM to SPN and the PP overlaps of different bonds that can be brought for your molecules. Hopefully yesterday and earlier today, you guys had a bit of time to just go through the remaining structures and try to assign the hybridizations. Now, it's important that on your own time or at your own time, you get to find time to do similar questions or just redo the same questions that we do together as a group, as an individual, where you just get a molecule, try and solve it to do the hybridizations, and then compare with what we had done, what you have for your notes, and then check if you are actually on the right path. With organic, the more time you spend solving, the better you become at it. It's a very simple course, but it just requires dedication. So you have to be dedicated, at least from the time you've started learning organic every day, irrespective of chemistry being on the timetable of what you're studying or not. It's a daily thing. Just find time to go through every day, do at least some organic. By so doing, you will not even, by the time you will realize, it will actually be very good when it comes to answering organic questions, because questions are normally repeated, and not only that, the concepts are the same, and the concepts will stick with more practice. You will tend to have very few complications. Okay, so I think I should have cleaned enough for us to use. So we need this space because that's the spaces that are a bit empty for us to use in the answering. That's why I need to clean that area before we begin class. All right, the area is clean. So we are coming to this particular question here. Draw and the draw the molecular orbital diagram, which is pictures for compound H. So compound H, where this is compound H that you have. The orbital diagram you're going to draw is a diagram that is actually going to show us how the overlaps are happening. Okay, it's a drawing that is going to show us how the overlaps are happening, which ones are add-on overlaps and which ones are side overlaps. So what you're going to do here is that this carbon, if you check, it has a sigma bond and a pi bond, and this side it has a sigma bond and a pi bond. This is a central carbon, so that's the carbon you're going to begin with. All right, so what you're going to do is you're going to get your carbon atom, put it there. That is your carbon atom, okay? And to the carbon atom, you put the s orbital, like that, and then you draw the P. So that is the P, and that is the P. So these two P, they should be of the same size. Okay, when you're drawing them, they should be of the same size. So these two P's that we have here are the SP hybrids. Okay, so this is the SP hybrid, and that is the SP hybrid that has this one here. So on the other side, you have the oxygen atom. So you put your oxygen atom, you also get that, and then you show the overlap. So you have that particular overlap. Okay, so in terms of hybrid, this is SP, this is SP2. So this is SP and this is SP. This is a add-on overlap. This add-on overlap is what forms a sigma bond. So this is a sigma bond here. So that is the sigma bond. So one of these bonds here you have defined. What has remained is for you to define the p orbitals that are overlapping. Now, the p orbitals that are overlapping should be in the same plane. So when you are drawing, ensure the angle at which you put the bond either on carbon or oxygen is the same. So I'll go at that angle, come. So these bonds pass here, it comes out like that and goes like that. So this is the unhybridized p orbital that I have. So the same here, when you draw the p orbital, it should be at the same angle. Okay, it should be at the same angle as the other one. So these are almost on the same angle, and then an electron. So there's an electron here. Okay, there's an electron in that p orbital, and there is an electron in that particular p orbital. And then here, there are electrons that are actually being shared in the forming of that particular sigma bond. And then these overlaps, you show them by dotted lines like that. Okay, so those dotted lines are what are representing the overlap. You do the same with the lower part. Now, if you check, I've not shown any electrons on the lower part because I have shown the electrons above there. So these electrons can either be up or they can be down. Irrespective of where the electrons are, these will still do what? Overlap. So this overlap is what actually forms a pi bond. So that is a pi bond. This is the double bond you are seeing there. What has remained on oxygen is actually that, like that, and like that. And you can put electrons there like that. And here you have electrons like that. So this is the oxygen atom that is sp2 hybridized. So you have dealt with this particular side. One add-on collision being made by sp hybrid and the side overlap. So these are the side overlap. After that, there is this carbon atom here. So I'll put my carbon atom there. I put that like that. You have that, and then you have that overlap. Okay, from that overlap, electrons being shared. So this is the sigma bond formed this side. You have shown one sigma bond. These orbitals, remember, this orbital here is sp2, is sp. This orbital is sp. Just like this orbital is sp. Okay, this orbital is what? sp there. This is sp2 because oxygen only has a double bond. So this is like an sp-sp2 add-on collision. This is like an sp and sp3. Why sp3? When you check this oxygen, this, I mean sp2, not sp3, sp2, because it has a side overlap. So this as that one in plane, you have to show another p orbital. So you put it at that angle, coming down and coming out like that. So it goes like that. This angle where it is the angle with which you also show your orbitals there. So try to draw your orbitals a bit better than this, like that. So there is an electron there, and there is an electron there. And then you show the dots for the overlap, okay? Like that. So you have that going all the way like that. And below the same, you have that and that. So that is the sigma, the pi bond, and this is the sigma bond that you have there. You have defined that. And then you have these other two bonds there for this particular one. And then there is a hydrogen atom on this one, okay, which is S, you put like that. And there is another hydrogen atom there. Okay, so, but for your hydrogen atoms, they should be not the way I've put, they should be directly this side. So they should be nicely drawn. So those are the S. So this is how the picture diagram, the picture orbital diagram is going to look like. This is how they want you to present your picture in form. So this is this particular molecule. This oxygen, that oxygen. This overlap giving us a pi bond. This add-on overlap giving us a sigma bond. This carbon, this carbon. This add-on overlap giving us a sigma bond, this add-on overlap giving us a sigma bond. That side overlap p orbital, that side overlap giving us the pi bond. These hydrogen atoms and the other hydrogen atom, this hydrogen atom and that other hydrogen atom. So everything that is in this molecule has been presented diagrammatically in this particular in this particular picture. So this is how this particular question was supposed to be answered. You label each CC bond in the compound E and draw the molecular orbital diagram for the compound H. So this is how your orbital diagram is supposed to come out when asked. Okay. Any questions that you may have, you can ask. Otherwise, we move on to the other part. Label each CC bond in compound E and arrange them in order of increasing bond length and bond energy. I think this one I had explained last time, yesterday, that the bonds that are being formed here can be sp2 hybridized or sp hybridized. And then depending on the length, depending on the type of bond that your molecule has, does it have sigma bonds or does it has a sigma bond and a pi bond? So the more bonds the molecule has, the shorter the molecule and the more the energy it will have. So check, you are dealing with compound E, which is this one here. So if you check, this is the triple bond. So this is going to be the shortest bond and the highest in energy. This is a single bond here. This is going to be the lowest in energy and the longest bond, as well as the strongest. Not only is it the longest, but it is also the strongest. The more the energy, the easier a molecule reacts. The less the energy, the difficulty with which the molecule reacts. So you have this one, high energy, low energy, high energy, shortest distance, longest distance, the in between these two. So the bonds, these bonds here. So if this is your carbon 1, your carbon 2, your carbon 3, your carbon 4. So C1 to C2 bond is actually the longest, the shortest, and the one with the highest energy. Bond C2 to C4 is the longest and the lowest in energy. C4 to C5 is the in-between. It is less in energy than the C2, but higher than the, triple bond, but higher than a single bond. And it is also longer than a triple bond, but shorter than a single bond. That is how you are supposed to handle 4. And then 5, write the expanded formula, which is the Lewis structures for the compounds A, E, and F. A, E, and F. So what you're writing is the Lewis structure, okay? So write the expanded. So you are writing the expanded, you are also writing the condensed. So for the expanded, I'll do for E, is it there? Yeah, for E, and then you do for Al and F. So the expanded, you begin with this carbon. It's a C. So that carbon there, C, it has a bond this side straight with a hydrogen atom. And then it has a triple bond like that with a carbon atom. So it has 4 atoms already. And then, oh, again here, this one has a single bond to a carbon atom there. This carbon atom has a double bond. If you check, it has 1, 2, 3 hydrogen carbon atoms, meaning there is an atom remaining that is going down there or up, which is a hydrogen atom. So if you check 1, 2, 3, 4, so the number of bonds of carbon atoms have added up to octet, and then you have carbon, so just 2 bonds, meaning you have a bond there and a bond there. This is the expanded. So in the expanded, all vertical and horizontal bonds are supposed to be shown. All carbon atoms are supposed to be shown. All hydrogen atoms are supposed to be shown. Any other atom present in the molecule is supposed to be shown. So if you check, all the bonds have been shown. When you draw a structure and you show all the bonds and all the atoms in a molecule, that is the expanded structure. Okay. For a condensed, okay, for a condensed, and that's a Lewis. So that's the Lewis structure, like that. And then for a condensed, the condensed structure 1, it doesn't show the horizontal and the vertical bonds, but it will show all the atoms present. Okay, so no vertical, no horizontal. In short, you're not going to show any bonds. So what you're going to do is you have H the way it is there. So you have H, and then you have C, and then you have a triple bond. So you don't need to show the triple bond. You just need to show that carbon atom. So you have that carbon atom, and then this carbon atom is followed by carbon and hydrogen, okay, which is this carbon and this hydrogen. And then this comes to carbon and 2 other hydrogens. So 2 other hydrogens like that. So if you are writing the condensed, this is the condensed C. So HC actually representing this one, HC, and then H, C, that is the C here, and then CH, that is the CH, and CH2, that is the CH2 here. So this is the condensed. In the condensed, you don't show the vertical nor the horizontal bonds. All you show are the atoms that are present. If a molecule has a substituent, that substituent is supposed to be put in brackets and in front of the molecule to which it is bonded. Okay, that is how you actually deal with the expanded and condensed chemical formulae for organic molecules. So, yes, Dolo. Your question?
Yeah, where it says write the expanded formula, and then we're answering question E, right?
They've given you A, E, and F.
Yeah, so right now we are answering E
Yes.
on the expanded formula. So I was asking,
yeah.
since we had, why didn't we have a hydrogen on the second carbon? And how do you know that each carbon should have an hydrogen, and the fourth, where are the hydrogens coming from? Like, how do you tell that this is where I put the hydrogen?
Okay. A carbon atom should have a maximum number of 4 atoms. If you are looking at a given chemical structure, from the structure, hydrogens, whether shown or not, as long as a carbon atom does not have 4 bonds, means it has a hydrogen atom attached. If there were any other atom attached, that atom is supposed to be shown. The only atom that is allowed not to be shown on a structure is carbon and hydrogen. Okay, so when I drew this, if you check this particular end here, they've not put any hydrogen atom. There's just blank. So this is where I'm starting. I'm saying this is where my carbon atom is. So this carbon atom here. But if I check, this carbon atom is having 3 bonds with the next carbon atom. But when you check these 3 bonds, this carbon atom is going to lack 2 electrons for it to be stable. You have 1, 2, 3. 1 bond is missing for this carbon to obtain octet. So if you check and they've not shown anything here, and there are no 4 carbon atoms to this particular atom, it simply means that there is a hydrogen atom missing. So that is how I knew to say there is need for a hydrogen atom to be put there. So in total, I have 1, 2, 3, 4 bonds to this particular carbon. Then this particular carbon becomes stable. So the same when it came to this carbon atom here has 1, 2, 3, but it is bonded to another carbon atom. So this is the 4th bond. There's no need for me to put a hydrogen atom here, because when I do that, this particular molecule is going to have more bonds than it should, which is wrong. Carbon should have a total number of 4 bonds. It never goes beyond 4 bonds. That is how I knew that this carbon doesn't need to be given any hydrogen atom. When it came to this carbon atom here, I only had 3 bonds. This bond here and these 2 bonds here. So these 2 bonds and that bond. So if I ask myself 1, 2, 3, and then there is a bond missing, as long as there is a bond missing that has not been shown on the atom, simply means that there was a hydrogen atom. So I have to compensate that by a hydrogen atom. That is how I am knowing which carbon is going to have a hydrogen and which carbon is not going to have a hydrogen.
All right, so I understand now.
Great. Okay, so I've done expanded and I've done condensed. Irrespective, condensed I've not done for F, but this is the F that you have. Irrespective of that, if you've understood how to do the condensed from the structure I've used, you can use the same principle to answer all these here as condensed structures. You can draw all these, just take your time and say, all right, I think I'm going to do a condensed, and write a condensed structure for yourself. Okay, that is how that is going to work. And then from here, you have the 7th, the 8th question that is asking, circle the functional groups for the compounds C and D and state to which class or classes of compounds the structure belong. Okay, circle the functional groups for the compound C and state to which class or classes of compounds they belong. So this is your structure C that you have. So since it's C that you have to identify the functional groups, all right? So if you check, you have any heteroatom that you get to have in your molecule. If your molecule has an heteroatom, it's highly likely that that particular heteroatom is a functional group. So if you check, there's an oxygen atom here, and then there is a double bond between carbon and an oxygen. This itself is a functional group. So this is a carbonyl carbon. Now, how you tell carbonyl carbons can form many different types of functional groups. So you have to know these functional groups and how they look like, okay? So every time the carbonyl carbon, which is carbon double bonded to oxygen, this is the carbonyl carbon. Every time a carbonyl carbon has this side and the other side, alkyl groups. If you have an alkyl group here and you have an alkyl group here, this functional group is going to become a ketone. That is, if this side you have alkyl, okay? If this side you have alkyl and this side you have alkyl group, okay? Alkyl group is a substituent if you are looking at an alkane. When an alkane is a substituent, it is known as an alkyl. You remove A and E from the alkane name and you just put YL. So that is why it is becoming alkyl instead of alkane. And then the substituents are going to be as such. So if you have alkyl groups attached from both ends, it's a ketone. If you have an alkyl group on one end and on the other end, you have a hydrogen atom. If you have a hydrogen atom like that, that particular end simply means that it is a what? A carboxylic, aldehyde. Okay, when hydrogen is attached on one side and one side of an alkyl group, that is an aldehyde. And then from here, when you have, instead of a hydrogen atom being attached, okay? So instead of a hydrogen atom being attached there, instead you have an hydroxide group, OH, like this. If you have an hydroxide group attaching itself there, this O becomes a group, and this group is known as a carboxylic acid. Okay, that group is known as a carboxylic acid. And then if instead of having a hydroxyl group attaching itself, instead you have X. So this X is a halogen. Okay, if this X is a what? Halogen. So if this X is a halogen, this particular group that forms is going to be called as an acyl halide. Acyl halide, meaning whatever has to come there has to end in ide. So if it is a bromine atom attached here, this molecule is going to become an acyl bromide. Okay, if what attaches there is a chlorine, it will become an acyl chloride. Okay, that is this functional group. And then from there, if it's not a halogen that attaches itself, if what you have is a nitrogen atom, okay? If you have a nitrogen atom like that, so this nitrogen atom, whatever else is going to attach itself there, it's not our concern. This nitrogen atom attaching itself to this forms an amide as a functional group. Okay, so the functional groups will just keep changing when you change the attachments here. If you remove this and you put an alkoxyl coming from the word alcohol, so an alcohol without a hydrogen atom, okay, so and then you have R representing any alkyl group attached to there. So this is an alkoxyl group here. This O group here becomes an ester. So as the functional groups are changing, the names are also changing. So these are the identifications you're going to start applying in this particular case of, in this particular question that we have here. So what you're actually going to do is circle the functional groups. After you've circled the functional groups, then you should name them. So if I check, this is the functional group. Okay, set, this is the functional group. Set, this is the functional group. Set, this whole thing here is a functional group. Set, meaning this molecule has 4 functional groups. And then you begin naming these functional groups. So when it comes to naming the functional groups, you can start with this one. This is O attached to this, but this O is attached to an alkoxyl this side. So I mean an alkyl this side. So this is like an alkoxyl attaching itself to the carbonyl carbon. So this is forming an ester. So what kind of group of molecules are these? These are esters. But not only are they any type of esters, these esters are cyclic esters. Very, very important type of esters. And if esters are cyclic, okay, if esters are cyclic, these particular esters are called as lactones. Okay, when esters are cyclic, they are called as lactones. So this is a lactone, but it falls under the class of esters. Okay, now because it is not any ester, it is cyclic. Now, because of its cyclic nature, this particular group is called a lactone. So you check, it is attached to a 6-membered ring. So this is cyclic. So this is a lactone. Okay, so it is an ester, but specifically a lactone because it is a what? Cyclic ester. We've identified what that is. When it comes to this one here, this is C triple bonded to carbon, carbon triple bonded to nitrogen. Whenever you have an atom like this with a triple bond, all right? So whenever you have an atom like this is called a nitrile. This is a nitrile, CN. Whenever you find the letter CN, meaning there's a triple bond between these two. Otherwise, they will put numbers somewhere. And once they put any other atom on this particular molecule, it's no longer a nitrile. Whenever a different atom appears besides these two, it is not a nitrile. It is only a nitrile when only oxygen and when only oxygen and nitrogen are combining. That's when we call it as a nitrile. Otherwise, it is not a nitrile. Okay, and then when it comes to this is the hydroxide. So this simply means that the name for that particular group is an alcohol. Okay, so that group there is an alcohol and therefore should be named as such. So this one is an alcohol. We've remained with one group, and I told you when N is combined directly to an atom that is a carbonyl, this is an amide. So what you have here is an amide. Okay. What you have here is an amide. Okay, amide. That is what this functional group actually is. That is an amide. Okay, so you have an amide, an ester, which is a lactone, a nitrile, and an alcohol. So these are the functional groups that actually make this particular molecule. From here, you can go to another molecule and try to just maybe say D, try to find out what these functional groups are, and you can name them for practical purposes. So that is how you show the functional groups. You circle, and then you do that. Okay, so like this molecule only has one functional group, which is this one here. So this is an alkyl, this is an alkyl, therefore this is a ketone in terms of naming what that particular functional group actually is. Okay, so it is cutting very soon. You can rejoin for an extra, say 10 or 15 minutes so that we can just wind up